Okay, so this is Dr. Sweeney, and this is the first part of our review for exam number 2, which is on quantitative distributions for variables. And so what I first want to talk about is we're first going to talk about discrete distributions, expected value, and the law of large numbers. This is the first section in this section of 4, and so it's important to help you kind of understand the basic terminology for understanding the later portions of this particular section. So let's first talk about the definition of discrete. And so what does it mean? We're going to look at discrete distributions. And so to be discrete is essentially it's countable. If you can count the number for the variable, right, then what we have is a discrete variable. And so like that's very basically stated. And so what we're going to look at right now for this section is only those for discrete variables, okay, and for made-up distributions, okay? So once we've actually talked about that, the definition of discrete, that countable number, now let's talk about what's called the discrete probability distribution, okay? And first is to notice that the random variable is going to be discrete, okay? So it's got a random variable that's discrete. And for each value of the variable, there is a probability. And so this is what it looks like. And so what we're looking at here is we're looking at, say, for example, like the number of siblings. All right. So let's say what we did is we asked everybody at the college, how many siblings do you have? All right. And so what we get is we get basically 24% of them would say that they have 0, 31% would say 1, 19% would be 2, 13% 3, 9% 4, and then 4% would say 5 or more. Okay. Now, given that that's the case, what we do is we think about, okay, well, what would that be as a probability? So the idea here is if I were to pick somebody at random from the population, what are the chances that they would say that they have 0 siblings? So the probability that they would say they have 0 siblings is 0.24. Okay, that's that idea. Is just like, oh, okay, do you have 0 siblings? 0.24. That's the probability that you'd actually somebody would say they in fact have 0. What's the probability that the person chosen randomly would say that they have 3 siblings? Well, that's 0.13. Okay. All right. So that's basically how these are set up. So for each value of the random variable, 0 siblings, 1 sibling, 2 siblings, 3 siblings, 4 siblings, 5 or more siblings, we have a probability of that occurring. Okay. So I might ask myself, well, what's the probability that x equals 1? And that's how we write it. We write, what's the probability that we have an individual chosen at random would say they only have 1 sibling? That's going to be 0.31. What about the probability that x is, say, for example, less than or equal to 2? Well, in this case, right, we would want to know those for 2, 1, and 0. So that would be 0.19, that's 2, plus 0.31, that's 1, plus 0.24, that's 0. And so that would end up equaling 0.74. Okay? And so these are kind of like some of the basic problems that we get for discrete distributions. What we're going to see is basically you're going to have a table or a layout, all right, that will ask you, that will give you probabilities, just like this one, and values for the random variable. That is, in this case, 0, 1, 2, 3, 4, 5. And what you'll have to do is you'll have to use that table in order to interpret the probabilities of certain random events occurring, right? Just like these. X equals 1, less than or equal to 2. We could choose probability that x is is greater than 1 and less than or equal to 5. Well, what about this? Now, this one's a little tricky because it says, well, greater than 1, does that mean 1 is in it? Well, no, 1's not in it because 1 actually isn't greater than 1. So in this case, this is going to be the probability that it'll be the probability of x equal 2 plus the probability of x equal 3 plus the probability of x equal 4 plus the probability of x equal 5. And why do we have the x equal 5 but not the 1? Well, that's because it's got the equal sign down here. Okay? And so that gives me 0.31, excuse me, 0.24 or 0.19 plus 0.13 plus 0.09 plus 0.04. And that equals, okay, 6.45. Okay. All right, so the probability of picking a person at random who has between, right, or has greater than one sibling, but less than or equal to 5 siblings, okay, or 5 or more in this case, is 0.45. And if you see this or more statement, what we're going to use for the value of the random variable is we're just going to use the 5. Okay, so you don't have to worry about, oh, should I put 7 or 9? Nope, just this value, just 5. Okay, so if you see that or more on the distribution, just utilize the number that's sitting there. Okay, now, one of the other things that we want to do is we want to notice, okay, so that kind of helps me to read or interpret the table, but how do I know it's actually a probability distribution? Well, how I know that is that I have 2 rules for it. The first rule is that the sum of all the probabilities in the distribution add to 1. Okay, and the second is that each probability is between 0 and 1. Now there's actually a third, and that's the values for the random variable are all represented in the table, and you can see in this case that's true because we have 0 to 5 or more. So let's check the other ones. Let's start with the sum of all the probabilities adds up to 1. Okay, so that's 4, 5, plus 12 is 17, 21, 30, there it is. And then we'll carry 3, okay, 3, 6, 8, 9, 10, there it is. It all adds up to 1. Okay, so that's the first requirement. And the second requirement we just have to check is each probability is between 0 and 1. All right, well, there it is, 0.24, 0.31, 0.19, 0.13, 0.09, and 0.04. They're all between 0 and 1, so we have actually the requirements for something to be a probability distribution. Okay, really important. One of the things that you're going to see in this section, and it'll come up more and more as we work on more statistics, is this idea of that there's a requirement for us to be able to utilize the math. Normally, somebody just gives you a problem and says, hey, you know what, go solve for x, right? Well, in this case, we're not just solving for x, we've got to actually do some work. We've got to figure out if we can use the math that we're going to use. And that's a big difference in statistics, and that's why we have these kinds of definitions, where we say, hey, is it a probability distribution? Because if it's not, we can't do what we do, what I just did. We can't actually find, say, and we'll look at this kind of expected value, we won't be able to do that, okay? And so consequently, we need to make sure that the rules are met. This one, fairly simple. There's really only 2 of them, okay? Sum of all the probabilities distributed add to 1, and each probability is between 0 and 1, okay? Now, next up is this idea of the expected value. Now, this is a distribution, and just like the distributions that we did inside of the last sections, we have a mean and a standard deviation. For the purposes of this test, you're not going to need to know how to find the standard deviation for a discrete distribution. It can be important for certain things, but in this case, we're not really going to need that. It's not going to be important for what we do. But this idea of the mean and being the expected value, that's actually a really important idea that we are going to need. And we'll talk about that in just a moment. Okay? Now, the idea of the expected value is this. If we take a single member randomly for the population, it could have any range of numbers of siblings in this case. So we pick somebody at random, they might have 0 siblings, or 1 sibling, or 7 siblings, right? And they're not all equally likely, right? How do we know that? We know that because the distribution here has that, the most likely amount of siblings we're going to get is 1 sibling. And the least likely is going to be the 5 or more, right? Because it has the smallest probability. But we could theoretically get any amount, all right, if we picked one of them. Now, what happens, though, as we increase the number of people that we pick out, right? So, let's say, for example, the first person we pick, they have 0 siblings. And the next person that we pick has 5 siblings, okay? Now, their average number of siblings is 0 plus 5 divided by 2. That's 2.5 siblings. Okay? What happens if we add a third? We have 0, we have 1 now, 5. Okay? We have 0 plus 1 plus 5 divided by 3. That's now going to equal 2 siblings, okay? And you can kind of look at what the math is here. What if we add a third one? Okay, 0, 1, 5. Oh, we got a 1 again. So this is now 0 plus 1 plus 5 plus 1 divided by 4. Okay, so that's 7/4, which actually is a bit less than 2. Okay, so what we get is that as we start to increase the number of, what we're going to do is we're going to increase the number of people that we select. We'll ask them, how many siblings do you have? And then we're going to take that average. All right, we're going to take the average, and that's what I did each step here. If you remember how you find it by hand, that's how you find the average by hand. 0 plus 5 is 2, 0 plus 1 plus 5 is 3, 0 plus 1 plus 5 plus 1 over 4, that's, okay, that kind of thing. The law of large numbers tells us that as I do this process, as I take an average over a long period of time, what it's going to happen is it's going to end up equaling the average of the distribution as a whole, okay? And what that is that's something going to be called the expected value. I expect to get the average every time I select another member of the population, right? Okay. And that just makes sense, right? If I know nothing else about the population, I expect the average. The average is the average. It's like the thing that, if you were to ask, the average height of a man at Santa Ana College is 5 feet 8 inches tall. If you were to pick a man at random, how tall would you expect them to be? And the answer is 5 feet 8 inches tall. Why? Well, because that's the average, right? The kind of our theory on this is that we're going to bunch up all the people up around the average. The most common value is going to be the average, and that's going to be our expected value, okay? And so that's kind of the idea, and where it gets valuable is in answering questions about what we might expect if we do an experiment, okay? So let's take a look and ask ourselves the question about the expected value for this particular distribution. And so when I ask the expected value here, what does it mean is if a person is picked at random, how many siblings would they have? How many siblings would you expect them to say? Okay, that's all that we're really talking about at this point. All right, so what we're going to do in order to find that, let me erase these notes in here. What we'd expect to do, or what we want to do in order to find that, is there's a formula that we utilize, okay? And it's pretty simple, and I've utilized this table in order to help demonstrate how to find these expected values. So what I'm going to do is I'm going to take this thing here, the 0, and I'm going to multiply it by 0.24, okay? So 0 times 0.24, and that is going to equal, that'll equal 0, right? And that's the portion of the expected value that we get from the people who say they have 0 siblings. So I now have 1 times 0.31. That's going to be the portion for those who have 1 sibling. So that's 0.31. 2 times 0.19, right? So that's the number of siblings, the value of the random variable, times its probability. So that's 0.38. 3 times 0.13, that's equal to 0.39. 4 times 0.09, that equals to 0.36. And then 5 times 0.2, or excuse me, 5 times 0.04, that equals 0.2. Okay? So what we now want to do is we just want to add these all up. Okay? So that's going to be 1, 8, 18, 24, 20, 24. So it's 2. Carry a 2. 2 plus 3 is 5, plus 3 is 8, plus 3 is 11, plus 3 is 14, plus 2 is 16, so it's 1.64. So this is my expected value. All right, so if you notice, the process that I went through in order to do that, and why I actually generated a table that looks like this, is to say, okay, so I'm going to take 0, right, the value for the random variable, times the probability, okay, and I'm going to do that for every value in the table. okay, for every single value of the table, in this case 0 through 5, and then I'm going to add them all together, and what I'm going to get is the value for the random variable. I'm going to get 1.64, that value. Okay, there it is. And so that's, if I ask somebody at random, how many siblings do you have? The answer that I would get or expect to get is somewhere between 1 and 2, right? Some will say 1, some will say 2. 2 is probably going to be a little bit more common, okay? Well, excuse me. They're going to say somewhere between, that's not what this is. If I were to pick somebody at random, I would expect that they would say something like 1.64, okay? And if I were to take many people, right, and ask them how many siblings they have, and then take that average, then what I would get is 1.64. Okay, that's my expected value. Okay, now let's talk about some applications of this. And this is the expected value problems. And if you remember, this is from 4.2. So an application of the law of large numbers and discrete distributions are these expected value problems. And so what we do with expected value problems is to construct a discrete distribution and then find the expected value, and that is actually going to help us to answer our question mathematically. Okay, so let's take a look at an example of this, and I'm going to help you develop a discrete distribution for it, right, to then find the expected value and then utilize that in order to answer this fundamental question. Okay, suppose that you are entering a raffle. There will be 500 tickets sold at a cost of $5 for each ticket. The first prize is $100. The second prize is $50. All other tickets win nothing. What is the expected value of a ticket? Should you play the game or not? Now, the method that I use for doing something like this is I'm going to actually generate a table, and my table is going to have all of the expected occurrences in it. Okay? Now, there are a lot of different ways of going about doing this, but this is the one that I use. Okay? All right. On the one hand, I have all my outcomes, right? That's my values for x. Then I have the probability that I'm going to get a value for the random variable of x equal to x. And then I finally have, because this is going to actually require me to find an expected value, I'm going to have x times p of x equal to x. Okay? I'm not going to do anything with that yet. I will in a moment. Then, in this case, I'm going to ask myself, well, what are the occurrences that I could have? All right? Well, the first one I could have is a first prize of $100. Okay? Okay? Now, trick here for the way that I do these is that you're going to have to remember that you're not actually just going to win $100. You're actually going to do 100 minus $5, which is $95, because you actually had to pay for the ticket. So for you, as a person who's actually doing this experiment, you've got to pay for the ticket, so it's going to cost you $95, or you'll make $95. 100 minus the 5 you paid for the ticket. Then, the next occurrence that we could have is 50 minus 5, which is $45. That is, you win first prize, okay, minus the value of the ticket, it's $45. And then the third thing that can happen, and this is where people forget a lot, is you could lose, right? This is not win scenario, right? Which is negative $5, right? You paid $5, you didn't get anything back, okay? Now, what about their probabilities? And that's all of them. That's all the occurrences. Notice we have first prize of $100, second prize of $50, third prize you didn't win anything at all, negative 5, okay? Now, what about their probabilities? Well, there are 500 tickets sold, okay? And only one first prize and one second prize, and then everything else loses. So we got 1 out of 500, which is 0.002. For the second one, for the first prize, it's also 1 out of 500, so that's 0.002. And then, not win, well, it's the other 498 of them. Can you guys see how I got that? That's 500 minus 1 minus 1, right? That's everything else that's left, okay? And so that's 0.996. Okay. All right, cool. So that's everything. Now I'm going to total it up just to show you that this is a discrete distribution. 0.002 plus 0.002 plus 0.996 is 1. That's everything. We got it all, right? Okay. Now, let's find x times p of x equals x. And what we're going to get here is the expected value of a single ticket. The expected value of a single ticket tells me how much I win or lose for every ticket I buy. Okay, so for every ticket that I buy, I either win this amount or lose this amount. Okay, and so if you think about it from the siblings perspective, the siblings was I pick a person at random, I ask them how many siblings you have, the expected value is 1.64. In this case, I buy a lottery ticket or a raffle ticket. How much money do I expect to gain or lose from purchasing that ticket? That's a really important question because it tells me whether or not I should play. All right, we'll see that in just a moment. So we start out with 95 times 0.002, okay? And then that's going to end up equaling 0.19, okay? Then we'll take 45 times 0.002, and that'll equal 0.09, okay? And then finally, we'll take 0.996 times -5. Really important that it's a negative there because you're losing money, okay? The values that we put into these expected values, they really do depend upon whether or not you or the person who's playing wins or loses money or makes money or loses money, okay? So negative you lose, positive you gain, okay? And so 0.996 times -5 is going to end up giving us -4.98. Now, just like the other expected value problems, I'll go in and I'll add them all together, and what I get is -470, -$4.70. So for every ticket I buy, every $5 ticket I buy, I expect to lose $4.70. Well, if you think about it, that's a bad play, okay? So this is a rule for you. Negative expected value means don't play. Don't play, don't buy the policy, don't do anything, okay? If you have negative expected value, you are going to lose on every ticket, right? Now, in this case, you might think to yourself, you know what? It's a charity. I'm giving to charity. I'm okay with losing $5. But if you're going to go into the casino and you're going to lay down your money, you don't want to go in there to lose, right? So consequently, if you have a negative expected value, right, that means don't play. Positive expected value, on the other hand, means that every time I play, I make money. So positive expected value means play. And that's an important distinction, okay? So we set up our discrete distribution, right? We find our expected value, and then the expected value answers the question, should you play the game or not? The expected value of the ticket, -$4.70, right? What that tells me, don't play. Let's try one more. Let's try one in another common example from expected value, which is from insurance. So an insurance company is going to take on a lot of policies. So they're going to do this a lot. That's like your law of large numbers. They're going to take on a policy, like lots and lots of policies. So any one policy might pay off because somebody could die, right? But then it's going to be offset by the one that doesn't pay off and who doesn't die, right? So they get to keep all the premiums at that point, okay? So what we want to do is determine if they're charging the right amount per premium. For the insurance company, that means having a positive expected value, right? Because they want to make money, so consequently, they want their insurance premiums to be positive, okay? Now, what that means is that the expected value should be positive. So we use a discrete distribution, and we find the expected value of the policy, and in this case, we're going to look at it from the perspective of the insurance company, okay? So, suppose the probability of death for a person that is given a particular life insurance policy is 0.005 within the next 20 years. In the case of death, the insurance company pays $250,000. The cost for the premiums for 20 years is $3,000. What is the expected value of the insurance policy for the insurance company? Okay, first things first, notice for the insurance company, and the reason why that's going to be important is because it's going to set up our positives and our negatives. Okay, so I'm going to set up my discrete distribution just to make this easier to visualize. Okay, I have an outcome, and I'm going to distinguish this as outcome, all right, and then I'm going to have a value for the outcome. And then I'm going to have the probability that x equals x, And then I'm going to have finally x times the probability that x equals x. Okay. All right. So now the reason why I put outcomes and I didn't put just like numbers like I did in the last example is because in this case, we've got two outcomes. And you kind of have to do a little logic here. From the perspective of the insurance company, you have to know that they only care about two outcomes because it's life insurance. They care about does the person live? Does the person die? There it is. Does the person live? Does the person die? Now, for the insurance company, if the person lives, they get to collect $3,000. So that's the value of if somebody lives. So the idea of a premium is if the individual lives, the insurance company doesn't have to pay out. They collect all the premium, $3,000. Cool. Now, what about, okay, if they die? In this case, it's going to be $250,000 minus the $3,000 that was taken in by the company based upon whether or not from their premium. Okay? So, or actually it should be this. It should be negative $250,000 because you're paying that out plus $3,000, right? The positive $3,000 is what they're taking in, and what's going out in the case of death is negative $250,000. So this is going to be negative $247,000. Now you're thinking to yourself, damn, that's terrible. Like, why would you ever have a thing where you could lose $247,000 and all you're bringing in is $3,000? Well, that's where the probability comes in. See, the probability of living, right, is 1 minus 0.005, which is equal to 0.995. How do we know that? Well, death within those 20 years is 0.005, so life is going to be 100% minus the 0.005. And then the probability of dying is 0.005. So it's way less common to actually have somebody, die within that 20-year period, and that's why you can pay out more. Okay? Now, my x times p of x, okay, so 0.995 times 3,000 is going to equal 2,985, and 247,000 times 0.005 is going to be 1,235, but it's going to be negative. Okay, so it's going to be negative. And then all we have to do is just add those two together. So we've got 2,985 minus 1,235, and that's $1,750. And notice it's positive, right? Positive expected value. So the insurance company, in the long run, if they write out a lot of different policies, in the long run, they will make 1,750 policies per person. They will make $1,750 per policy per person. So we might ask a question, and this is, I don't think this is going to be on the exam. You know what? It's not going to be on the exam. But it is at least something you should think about. If I had 2,000 people, you know what? It might be on the exam. How about that? If I had 2,000 people with a policy, how much would I expect to make? Well, here's how this works. Since I have 2,000 people who have a policy and the expected value per person is $1,750, the answer is 2,000 people times the $1,750. Okay. Which ends up being so the answer is $3.5 million. Okay? So you can see why insurance companies want lots and lots of people with policies, because if they just have, a relatively small expected value, right, per person who writes the policy, then what that'll tell you is that it'll actually tell you that how much they will make for all of those policies all put together. Okay? The expected value is how much they get per individual, right? And just to reiterate, something like this could be on the exam, maybe as an extra credit problem, all right? There's an Easter egg for you, for those of you who are actually watching the videos. All right, cool. Bye. So with that stated, we've got what we need to know about about discrete distributions, expected value, and the law of large numbers. Essentially, what we're looking at here is we're looking at distributions that are going to be generated for you, or that are relatively simple and that you have to generate yourself. Each one of the distributions will have a value for the random variable, like 0, 1, 2, all of these, like these values here, and a probability. To find the expected value, you'll multiply the value for the random variable times the probability for every value in the distribution, and then add them all together. What that means is it's the value that you are going to get for every one play, right? Each random ticket, okay? Or, so like, for example, for the 500 tickets that we get, we can actually find how much money, right? How much money will the company make, or will the raffle make? And that'll be negative $4.70 times the 500 tickets. Okay? Because that's per ticket, per one ticket. And this is 500 tickets. All right? So that's what that expected value is. It's how much you get for every one time you do the event. For every one person you pick at random, or like in the case of the insurance company, for every policy that they write. Okay? All right. I hope that helps you out in terms of kind of reviewing for this portion of the test. It's pretty straightforward. There's only a couple things that you'll probably be asked to do. If you have questions, please send them to the discussion board or email me directly, and you should be able to. These are very similar to the ones on the review. Okay? All right. That completes this.